Welcome to today's explainer. Look, if you're a first or second year computer science student currently wrestling with C programming, you are in the exact right place. Today, we're taking two concepts that can honestly feel a little abstract, stacks and recursion, and we're going to connect them directly to their practical implementations in C. We're literally popping the hood on your computer's memory to see exactly how these ideas power the software you use every single day. I am super excited to guide you through this, so let's dive right in. Okay, here's our roadmap for today. We're going to start with the stack data structure, then look at implementing stacks in C, explore the call stack, demystify recursion, trace recursive functions under the hood, and finally wrap up with some crucial traps, tips, and takeaways. All right, section 1, the stack data structure. So to really grasp this computer science idea, just think about everyday objects. Imagine a deck of cards or a pile of plates in your kitchen. If you're putting away a clean plate, where do you put it? Right on top. And when you need a plate for dinner, which one do you grab? The one right on top. You're definitely not trying to yank one out from the middle or the bottom, right? Well, a computer science stack behaves exactly the same way. It's simply a linear data structure that allows you to add or remove things at one end only. And that brings us to a huge acronym you absolutely need to wire into your brain, LIFO. Last in, first out. It dictates every single stack operation. The most recently added element, the absolute last one in, is always going to be the very first one taken out. Once you truly internalize this golden rule, you've unlocked the core of how a stack operates. To actually use this LIFO structure in C, we rely on a very specific vocabulary of core operations. We push to add an element to the top, and we pop to remove it. If we're just curious and want to look at the top element without actually removing it, we use peek. And to make sure we aren't breaking anything, we use utility functions like isEmpty to see if the stack has nothing in it, and isFull to check if we've hit our maximum capacity. Notice how push and pop literally move data in and out of that single open end of our container. Check out the top pointer there. We constantly maintain this pointer to keep track of the very last thing we pushed. When we push an element, that top pointer moves up. When we pop an element, it moves back down. It's incredibly straightforward, but highly efficient. Moving right along to section 2. Implementing stacks in C using arrays. So, transitioning from the theory to the actual C code, our very first step in an array-based implementation is to initialize our top variable to -1. Why -1? Well, C arrays use zero-based indexing, so -1 clearly indicates a completely empty stack. When we want to push, we first check if the array is full. If we've got space, we increment top by 1 and insert our value at that new index. Popping is just the reverse. Check if it's empty, grab the value at the current top index, and then decrement top by 1. Since we're essentially just doing basic math on an index and accessing an array, these operations happen in constant time, big O of 1. Honestly, it's incredibly fast. But you know, that kind of speed requires serious discipline. Listen up, because this is where things can go horribly wrong. Static arrays in C have a fixed size that is allocated at compile time. Pushing an element onto a stack that's already full causes a stack overflow. On the flip side, popping from an empty array causes a stack underflow. If you get lazy and ignore your isFull and empty checks, you are practically asking for memory corruption, segmentation faults, and totally undefined behavior. You have got to handle your boundaries. Section 3, the call stack and function management. Let's shift our perspective for a second. Instead of building a stack ourselves, let's look at how your operating system uses them dynamically. Because stacks are literally everywhere in software. When you hit undo in a text editor, you're popping your last action off a stack. Clicking the back button on your web browser, that's popping URLs off a history stack. Stacks are used to evaluate math expressions and even solve complex mazes. But for us C programmers, the absolute most critical application is function call management. Your machine's memory manages function calls meticulously. Every single time a function is invoked, the computer generates what's called an activation record. Some people call it a stack frame, and it pushes it right onto the call stack. This record stores all the function's local variables, its parameters, and crucially, the return address. That address tells the program exactly where to pick back up when the function is done. Once a function completes, boom, its activation record is popped off the stack, and its local variables are destroyed. All right, section 4, demystifying recursion. Computer science's ultimate magic trick. Now that we have a solid grip on how the call stack actually works, we can finally tackle recursion. Recursion relies entirely on that stack. In plain English, recursion is just a programming technique where a function calls itself. It's a way of solving problems through repetition and self-reference. So instead of writing a clunky while or for loop, a function tackles a massive problem by slicing off a tiny piece and handing the rest of the problem to a brand new copy of itself. But here's the catch. Every valid recursive function has to have two parts. First, the recursive case, which is where the function calls itself with a slightly smaller argument. But second, and this is absolutely crucial, it needs a base case. This is the simplest, smallest instance of the problem that can be solved right then and there without needing another recursive call. The base case is your exit strategy. It guarantees the function will eventually stop. I cannot stress this enough. If you forget your base case, you are guaranteeing infinite recursion, and your program is going to crash hard. Section 5. Tracing recursive functions to see what's happening under the hood. Let's make this concrete by tracing some real C code. Calculating a factorial is the classic example here because the math translates perfectly. The mathematical formula is n factorial equals n times n minus 1 factorial. In C, our base case is simple. If n equals 0, return 1. Our recursive case is return n times fact of n minus 1. Now remember the call stack we just talked about? If you call fact 4, it can't just give you the answer. It has to call fact 3 and sit there waiting for it. But fact 3 has to call fact 2. And wait, every single one of these calls generates a brand new activation record, stacking up in memory. Walk through this table with me. It's fascinating. See how fact 4 is stuck in the waiting on column? The stack just keeps piling these records higher and higher. Fact 4 pushes, fact 3 pushes, fact 2 pushes, fact 1 pushes, and then finally we hit fact 0. That's our base case. It doesn't call anything, it just straight up returns 1. Now watch LIFO in action. The stack begins to pop. Fact 1 takes that 1, multiplies it by its own n, which is 1, and returns 1. Fact 2 takes that, multiplies by 2, returns 2. Fact 3 multiplies by 3, returns 6. And at last, the original fact 4 takes that 6, multiplies it by 4, and returns our final answer, 24. The whole cascade resolves sequentially, in perfect reverse order. Section 6. Traps, tips, and takeaways. Let's make sure you ace your next exam. You are definitely going to see this comparison in interviews. Iteration versus recursion. Iteration is your standard for or while loop. It takes up way less memory and usually runs faster. Recursion, on the other hand, relies on a function calling itself. It can make crazy complex code look incredibly clean and readable, especially when you're working with trees or graphs. But remember those activation records? Because every recursive call adds a new frame to the call stack, recursion is super costly when it comes to memory and processor time. Which leads perfectly into a classic interview trap. What actually happens if you forget the base case in your recursive C function? Well, without a base case to apply the brakes, your function just keeps spawning new activation records. It pushes and pushes and pushes, relentlessly consuming memory until your system's limited stack space is totally wiped out. And when that happens, your program dies instantly with a fatal error known as, you guessed it, a stack overflow. So let's bring it all together. Stacks are strictly last in, first out. When you're coding them with arrays in C, always start your top index at -1 and be completely paranoid about overflow and underflow boundaries. Deep down, the system's call stack is what manages your program's flow. It's the engine that makes recursion possible in the first place, as long as you always provide a base case. You guys have absolutely crushed the fundamentals today. But before we close out this explainer, I want to leave you with a bit of a challenge. Today, we built a stack using a fixed static array, meaning there's always that looming threat of a stack overflow if we run out of room. So, how might you design a stack dynamically using a linked list? Think about it. How could you use pointers so that your stack can just keep growing infinitely, avoiding capacity limits altogether? Mull that over because that's your bridge into your next big data structures topic. Thanks so much for joining me today. Keep writing that C code, and I'll catch you in the next one.